In this video, we'll demonstrate how 5G library is elevated with our 3GPP compliant NTN channel model. NTN communication system engineers face a new set of challenges. In non-terrestrial network systems, the considerable distance between the GNOB and the UE results in large path losses and notable propagation delays. Due to the rapid relative movement between spaceborne vehicles such as LEO satellites and the UE, the velocities can exceed 7 km per second. So, the Doppler shift for a 2 GHz carrier frequency can be more than 20 parts per million. Our 5G NTN model provides flexible trajectory coordinate entry, integration with existing workflows, and unique orbit and channel visualization. Define spherical orbits with the spherical mode, but select classical for more options. Here, you have 7 settings to define the non-terrestrial platform trajectory and its position on the orbit. The two first settings define the size and shape. The following 3 parameters are related to orientation. The true anomaly setting allows you to define the position of the platform on the orbit. Epoch, date and time are used to translate the trajectory definition to the Earth fixed frame. The model also lets you to upload EOP files for a more informed frame translation. You can import SDK files and ASO files. You can monitor the channel characteristics while you visualize the trajectory. There are 6 kinds of path losses defined in this model. Delay, Doppler, and path loss can all be sent to a dataset from the visualizer. In this bent pipe design, we employed 2 5G NTN models, one for the feeder link and one for the service link. The satellite functions as a signal mirror. I am transmitting a single RF tone at 28 GHz. Analyzing the spectrum reveals the Doppler effect. Frequency decreases as the signal moves away and increases as it approaches. In time domain, we can see delay. We now transmit a 5G NR signal. The gateway upconverts the signal. The signal processing in the compensator subnetwork will compensate for delay and Doppler. The signal at the UE input cannot demodulate due to Doppler. After the compensator, it demodulates successfully. For budget analysis, we like to measure the receiver sensitivity, which tells us the receiver's ability to effectively demodulate data in the poorest radio conditions. I configure 2 receiving chains in the 5G NTN channel model for a 1x2 SIMO setup. Power sweeping indicates that achieving over 95% throughput demands minus 123 dBm over 15 kHz. This yields a sensitivity of minus 88 dBm. Sensitivity and path loss will determine the antenna EIRP. We achieve this EIRP with a 4x4 array. Lastly, we will look at time drifting. The path delay presents an initial long delay, but also time drifting. The latter can cause inter-carrier interference, as it may lead to loss of orthogonality among OFDM subcarriers due to sampling clock error. This issue becomes more critical in the context of a 5G NR signal with a dense modulation and coding scheme. We compare the receiver performance without time drifting compensation with frequency domain phase rotation compensation and with time domain resampling compensation. Without any signal processing to compensate, the constellation exhibits phase rotation. Both algorithms do well at compensating time drifting induced phase rotation. You can also bring your own signal processing to compensate for time drifting. I will add this signal processing to my comparison. In summary, we've demonstrated how the end-to-end model allows you to validate your design with compliant models and show feasibility earlier. Thank you for watching.